So let us complete the mass capacitance in the last class we have seen. Okay, so here the gate capacitance, when we talk about the gate capacitances, we also considered previously the length is also a fixed quantity, but we don't do that kind of thing. Okay, just we take it as the length is on our side. Okay. Okay, therefore we keep all this length is also will come into the point. But gate overlap capacitance, because XT is a constant, okay? It is a manufacturing, whenever they manufacture something, how much it is lateral enclosure, that is actually a fixed quantity, okay? This particular length is a fixed one. That's the reason why it is possible that we can make this is the length of that particular extension is a constant, okay? What is the last capacitance we have to think about it? Junction capacitances, okay? So just I want to give the junction capacitance. Okay, so we can see that the junction capacitance here in this way. Okay. Here we have a source. Okay. Here we have drain. Oxide inside of it, right? Okay, therefore this capacitance is actually from the body to this one, right? Okay, there is a body, right? So body to source and drain to body. Okay, so this is what the capacity, this is what junction is available here. You can consider it in this way. Okay, therefore there is a PN junction is formed there. Whenever there is a PN junction, that too it is a reverse biased. When the PN junction is in the reverse biased, definitely the capacitance can be seen. That capacitance is called junction capacitance. Okay, so here actually this capacitance has two type of capacitances we can see. One capacitance is called sidewall capacitance. Sidewall capacitance. The second one is called bottom capacitance. Bottom capacitance. Okay, so you look at the source side, for example, look at this is what you can normally observe. Okay, for example, assume this is the three-dimensional view of your source. Of course, this I'm writing all these are sharp edges, but it's not a sharp edge, right? Okay, what is the bottom here in this case? The bottom is actually this one, right? The bottom is this one. Okay, that is actually with the substrate, that particular bottom with the substrate will see some kind of capacitance. It is just a junction capacitance. Similarly, sidewall means these are the things will come into the sidewalls. Okay, all these things will come into the sidewalls for all the directions. Is that point is clear to everyone? Okay, so therefore we need to calculate that capacitance also. As we talked about previously also, what is this capacitance? Is a junction capacitance. Okay, we take one simple structure, something like this. For example, this is the diffusion area. This is the polysilicon area. Okay, and the polysilicon width is something like this. The width of the polysilicon is something like this. This is the width. Okay, so this is the extension is called E, and this is the extension is E. So when we talk about the bottom capacitance, okay, this is called, this is C source to body or C drain to body. Both are the same. Okay. It consists of two parts, bottom capacitance and sidewall capacitance. Okay. The sidewall capacitance we can write the width of the E into Cj naught divided by 1 plus Vd divided by pi over Mj plus. Okay, next sidewall capacitance is 2E plus W. So actually not suffix C, W into E. Here actually 2E plus this one into C is something like this, I can write sidewall and Vd divided by pi whole power MJSW sidewall. Better is the sidewall means I can write it as W. Usually bottom capacitance is actually step graded. Okay. And sorry, bottom is actually step graded, but sidewall is actually linearly graded junction. Okay. Step graded junction. Something like sweeter. Okay. So these are the available capacitances we can see for the MOSFET. Okay. Of course, these capacitances are more considerable when we are operating in the MOSFET in saturation. Okay. Whatever the capacitances that we see in the saturation will results the bandwidth of the amplifier that we are going to design with MOSFETs. Okay. So the most important thing is that, so when the MOSFET is in saturation region, what capacitances that we can see is the very, very important for us. Not necessarily considered all the capacitances. Okay. So, okay, therefore we can conclude that we have a gate capacitances, gate overlap capacitance, and junction capacitance. These are the three type of MOS capacitances we can see in the MOSFET. Right. So I'm going to stop this one now. Let us go and look at another concept. This is the lecture number 16. Small signal model of a MOSFET. So already we have seen what is the small signal model of a MOSFET, N-channel MOSFET. So that means that here the small signal means what? So when compared to the DC operating point, this value is very, very small. Okay, that means a small change in the given applied voltage. Okay, so therefore, under that condition, MOSFET can be looked at a linear element. Normally, MOSFET is a non-linear device, but we can make it as a linear when we apply a small change. Okay, under that condition, we apply this transistor, right? Under that condition, if this is your N-channel MOSFET, gate, drain, and source, we can make this is equivalent to something like this. What is this current equation? What is this current? So we apply here is a drain. Here is the drain. Here is the gate. And here is source. Here is body. Okay. So what is this potential that we apply here? The small change is VGS. what you will get here? GM into VGS. Similarly, what is another equation? What is the one another current equation or current device? This is because of this potential difference, right? This is because of this potential difference. Of course, I'm so sorry. It is a negative potential, right? It's a negative. This is a positive. This is a VBS. It is a body to source. Okay. Therefore, this is called GMB into VBS. Similarly, we have another component. What is this component? Resistance. That is called R naught. Okay. What is the dependency of this one? It depends on VBS. Is the point is clear to everyone? Okay. If this is the current is flowing here, this is what the current is flowing here. This is called ID. Therefore, this ID is actually due to the change in VGS, due to the change in VBS, due to the change in VDS also. Okay. Now let us look at one important point here. Okay, let us take some scenarios. How do we calculate the resistance offered by that particular MOS transistor? Okay, let us look at this particular scenario. For example, this is what load transistor, example number 1. Find the resistance of a MOSFET as mentioned there. Okay, not a problem. We'll look at that one. For example, here we took it to one MOS transistor. Okay. So this is connected to ground. The body is also connected to ground. And I'm applying here is some bias potential. Therefore, this is called VB. VB I'm applying. VB. And I want to see, just I want to stand here at the drain and I want to look at what is the resistance offered by this MOS transistor. I'm stand on the drain potential and I want to see how much resistance can be seen by the MOS transistor. Okay, right. So now, as we know that for the small changes in this one, we can see the resistance, right? Okay. Now we have this potential. Sorry, we have this particular short channel, what we can call it as a small signal model. We want to consider that. See, whenever you would like to calculate the resistance at a particular place, you have to get this one by using this approach. Okay, connect one potential here plus or minus Vx and find Ix and take the ratio between the Vx divided by Ix will be the resistance at that particular point. Is the point is clear? Okay. Now, please observe that if you want to evaluate the resistance of a small signal model, something like this, first thing is that there should not be any kind of bias points. DC voltages should not be there. There should not be any kind of DC voltages. So what is the DC voltage here? This is what the DC voltage. Therefore, this should not be there. Okay, that means we have to make it as a 0. Okay, so therefore, what I'm going to do here, I'm going to make this is a 0. If this point is clear, first of all. Okay, if I make this is 0, what it will be influenced? If the gate to source potential is not there, okay, then what is happening here? There should not be any This won't be there. Okay. Okay. Now the gate and source are at the same potential. What does it mean? It's just like a short circuit, right? It's just like a short circuit connected to ground. That means this potential is also not there, right? This potential is also not, this particular current source is also deactivated. This point is clear or not? Okay. Now only we can see R naught. Now what is this one? You can tell me. What is this Vx divided by X ratio? It is simply something like this, right? It is already grounded. It is grounded. It is actually plus or minus Vx, small Vx. Okay. Therefore, this is a Ix. Here we have I naught. What is the value? R. R is simply R naught. That is Vx is across R naught will be there, right? Huh? Therefore, what is this current actually? Why? Because since what? I is actually Ix into R naught is equal to Vx. Therefore, Vx divided by X is nothing but R naught. Okay. This is what, please remember. If I take a MOSFET something like this, if I ask you to find out what is the resistance from the drain, okay, then what should be your answer? It should be R naught. What is R naught? What is R naught? The last class we have seen that one. You forget about that one. Lambda times of ID. This value is approximately 20 kilo ohms. Usually it's 20 kilo ohms. Of course, I have not mentioned anything about the D, but usually it will be there 20 kilo ohms around. Okay. Right. For example number 2. We have a transistor something like this. I'm connecting the gate and drain something like this. And I ask you to find what is the R here from the drain potential. Again, we stand here. We want to look at from the drain to see what is the resistance offered by this. Okay. And assume that this is connected to ground. This is also connected to ground. Both are at the same potential. Okay. That means that there is no body effect. When the source and drain body are at the same potential, we don't have any body effect. Okay. So what should be this particular case now? Okay, let us go and use this particular. What is the unknown things here? Okay, again, we want to look at the drain. Therefore, drain in the drain place, we have to keep it one source, right? Keep it the source there. Okay, let me take this one better. Plus minus. Therefore, this is called Vx. It is called Ix. Okay. What is this? What is the thing here? What things should not be there here? We don't worry about this one, right? Okay, this is not there. And what is the connection here? Gate and drain are shorted. Gate and drain are shorted. Okay. Do you have any body effect? There is no body. That is the reason why we kept that reason actually 0. Now we have only this equation. Can you please tell me how do we replace VGS in terms of Vx? What is the VGS? If you know the VGS in terms of Vx, then I can definitely I will calculate that one very easily. Okay, this potential is actually gate potential, right? This potential is also the drain potential. Am I right? This is what the drain terminal, right? This entire thing we can call it as a drain terminal. So, but actually, according to the drain and gate are shorted together. That's the reason why gate at that point is gate potential is equal to the drain potential. At the same time, you can see Vx is also available here, right? That is actually, it's a Vx only. It is actually Vx only. Okay. Therefore, you can observe this one. VGS is nothing but, what is the VGS? It is also can be called as VDS. Why? Because source is at the ground potential. You observe this one. Instead of VD is equal to VG, VGS is equal to VDS equal to aperture. We can say that one. Why? Because the source at the ground potential. That is also equal to what? Vx. Okay. Now, so therefore, can we replace this one with the help of Vx, right? We can write like this. Okay. Now, what is this particular one? You can we can simplify this one. There is a one current source here. There is one resistance here. Okay. So both are at the ground. Both are at the ground. And this is actually Ix is coming from here. And we have, we need to calculate, we need to apply Vx here. What is this? You're not able to write properly. So what is this one? This is a Gm into Vx. This is a R naught. Can you tell me what is the ratio between Vx divided by X? And what is this one? Therefore, Ix is equal, the current is actually, this current is equal, for example, I1, this current is equal to I2. Let me consider it in this way. Okay. Therefore, Ix is I1 plus I2. What is the I1? Gm into Vx. What is the I2? Vx divided by R naught. Right? What is this? Can you please tell me what happened to the Vx divided by X? Is equal to what? 1 by Gm plus 1 by R naught. Right? Usually, as I'm told you that R naught is actually 20 kilo ohm. Okay, approximately. If 1 by 20 kilo ohm is very, very small in number. Therefore, we can approximate this resistance R is approximated as 1 by Gm. Okay. This is approximated as 1 by Gm. So therefore, in the circuit designing point of view, if I say that what is the resistance for a diode connected load, this is called diode connected load. If I ask you this question, immediately you should say it should be 1 by Gm. The MOSFET offered by the resistance value is 1 by Gm. Diode connected load. Okay, so diode connected, this is what the diode connection. Okay, so whenever you use the gate to the drain, this is called diode connection. Okay, point is clear to everyone? Right. Now, let us take the third example. For example, example number 3. I have something like this. I want to calculate, I want to stand here at the source and I want to calculate the resistance from here. Okay, at the source. And assume that this is at the ground. And assume that these two are connected, something like this, connected to VDD, for example. It is connected to VDD. Gate and drain are connected to VDD, but the source is not current somewhere. But from looking at the source, how much resistance that is given by the, mass transistor? Okay, because the resistance offered by the mass transistor is very, very important for us. Because we have to pass that resistance to that resistive network, and then we'll get the maximum gain. Okay, so therefore, it is required that how much resistance offered by the mass transistor. Okay, so now we stand at the source place. Okay, now let us go and analyze this one. Okay, this is what the MOSFET model. Okay, so what are the connections? Please let me know. So what about the gate and drain? Both are at the same potential, but okay, both are at the same potential. Okay, let me come here. But what it is, what it must be connected? Ground, because it's a VDD, DC source. That is, VDD is a DC source. Whenever you see the DC source, you have to go make it as a 0. Okay, so this is also connected to whom? This is also connected to 0, because this entire thing is actually a drain potential. Gate and drain are at the same potential. Are you getting the point? Okay, but what about the body? Body is at ground, fine. Body is at ground, fine. But if you want to find out the resistance here, what is the condition? What we are doing so far? We kept one voltage source there and allow the current flowing through it, and we take the ratio between the Vx divided by X gives you the resistance value. Same thing we could do here also. Keep it here, a source here, sorry, not source, plus or minus here. Okay, this is called Vx. Okay, what is the current flowing here? Ix. Okay, now what is this Ix here? You can see this Ix is actually, as you carefully observe, this Ix is actually one current is flowing here, current is coming here. Okay, let me call I1, let me call I2, some current is flowing here. And this is actually going in this direction, I3. Look at this one. The current is always going from the resistor positive terminal to the negative terminal. Ground is at the negative terminal. This is at positive terminal. If you suppose, what is the best way to solve this problem? What is the best way to solve this problem? So first of all the currents are contributing. Okay, GM into VGS and GMB into VBS is also will come into the picture. Okay, that means if you are able to remove the VGS and VDS with respect to the VX, then things will come to our hands. So how do we replace VGS and VBS in terms of the VX? Okay, look at this on the input side here. This side you can see this is actually less VGS. It will start here at negative, minus of VBS is equal to 0. Okay, voltage law. Did you catch this point? This is VBS. This is, sorry, VGS and VBS. Okay, accordingly, what is the value of the VGS? VGS value is equal to VBS. Agreed? But what is the VGS? Sorry, what is the VBS? What is the VBS? In terms of VX? This VGS is actually the Vx only, but it's a negative polarity. Observe this one, this is a negative actually, this is a positive. But what potential we applied? Positive here, negative here. What you will get here? Minus Vx. Therefore, this is also equivalent to say that VGS, am I right? Therefore, VGS and VBS can be replaced with minus Vx. Getting this point? Okay. Now, therefore, simply we can remove this particular portion. We can remove this particular portion. We can place this as a minus Vx. Of course, I don't want to do it here. Okay, let me consider, keep it as it is. Okay. And look at this point carefully. There's many ways that we can do this problem, but very simplest way, let us go. So this is the current equation that I can write in this path. Therefore, I start from this B to drain. Okay, look at this small fundamental. Here, there is a one node is available here. Here, one particular path is there. One current is coming from here that is called IX. One current is coming here that is called I1. The second current is coming from I2. And one current is going here called I3. If I want to calculate I3, what I can do? Anyone in the class? So they are all connecting at the one point only. Okay, but different branches that are there. One current is coming to that particular, one branch is coming to that point. Three branches are there, already above three branches are there. Two are inside and one is going up. I want to calculate I3. What is that one? What I can do? So what I can do? IX, what are the coming here? Coming point? IX plus I1 plus I2 minus I3 equal to 0. Therefore, what is the I3 here now? I3 is nothing but IX plus I1 plus I2. Same thing I can apply here. Okay, I know this potential. KVL I'm applying here. I know this voltage here. I know voltage here. And I can calculate what is this value. Okay, look at carefully. Minus Vx. This is one voltage. What is another voltage I'm writing here? R0 into I3, right? R0 into I3 equal to 0. What is I3 here? What is the I1 here? What is the I1? Yes. GM into. Oh, so first of all, IX trial kada first. What is the IX? IX is same IX only. Plus GM into VGS plus GMB into VBS equal to 0. Are you agree with me? Okay. So little bit network theory is required. Okay. Now what is happening here? What is what we can replace? Minus Vx. Okay, Vx plus R0 is R0 into Ix plus what is this value? GM into minus Vx plus GMB into minus Vx equal to 0. What we can do it minus Vx common this one. We can take it common 1 plus G. Okay, R0 into GM plus GMB into R0 plus R0 into Ix equal to 0. Can we write like this? Huh? Just I kept it. We taken away Vx is a common. Okay. It is possible that this value is far more higher. Okay. Okay. R0 is actually 20 kilo ohms. 20 kilo ohms to GM is also a big number. Altogether, the product is a big value. So it is one is very smaller than that one. That's the reason why I can remove one. I cannot remove GM. I can remove one. Okay. So therefore, what I can do minus Vx is R0 into GM plus GMB is equal to, okay, not is equal to what I can do. I keep it the other side. Is equal to R0 into Ix. Therefore, Vx divided by Ix equal to R0 divided by R0 into GM plus GMB. Okay, R0 and R0 will get cancelled. What is the resistance can be seen there? 1 by GM plus GMB. It can be approximated, right? So therefore, when looking at the source, what is the resistance offered by the diode connected transistor? 1 by GM plus 0. Okay. Is that point is clear to everyone? Okay, we can take last example and we can leave. Okay. We'll take a simple example. Okay. Example number 4. We look at this is the transistor. Find the resistance seen from the drain if RS is connected at the source. It is actually plus or minus. This is VB. Okay. Now, can you please someone calculate this one? What is the resistance seen from the drain when a source resistance is connected at the source? I will give you as a homework for after some or another question. But please look at this one. Okay, take it first of all. So what is the connections we have to think about here? First thing. Okay, if I'm not giving anything here, please remember that one. There is no body. The body is connected to ground. Okay, look at in this way. Right. Okay. Now, what is the gate here? Gate must be connected to ground because the DC source is connected there. Okay, fine. And I need to provide. Okay, there is a. What should I write here? I want to calculate the. From the drain, I want to calculate the resistance. Therefore, I keep Vx here, and I want to calculate Ix here. Okay, the ratio between Vx divided by X I want to calculate. Okay. Now, where is the resistance here? Here is the resistance Rs that is available already. The body is connected to ground. The body is connected to ground. How do I replace VGS and VBS? How can I replace VBS and VGS? As you closely observe, this Ix will flow from here. It is also flow from here. It is flowing through this one, and it will reaching to this point. Can we say this is Ix? Okay, because that is the path. It is source is coming from here, and it will be distributed at this point. They all mix together, and will come out of that. Okay. Okay. So what is the VCS here now? And you can look at the input side. What you can see at the input side. Less VCS minus of VBS is equal to 0. Okay. Or I can say that VCS is equal to VBS. Am I right? What is the VBS here? What is the VBS? Anyone? What is the VBS? Huh? Ix is multiplied with Rs. But where it is coming from VBS actually? Okay, keep it like that only. So what is happening here? It is come from Ix into Rs. Okay. So now accordingly, this is the same way that we have seen the previously also. So this current is going through this particular one and will go in this way. This is the easiest path. Okay. So what did this path says that? What is this path? Minus Vx, it will start from minus negative terminal, and then R naught is multiplied with what? R naught is multiplied with what? What's happening here? Careful, you have to be very careful. So therefore, the one current is flowing here, for example, I1, this is I2, this is I3. I want to calculate I3, but all this thing is coming from Ix. What is this value then, I3? I3 is Ix minus of I1 minus of I2. Right or not? Okay. So therefore, I'm going to write this one. What is the Ix here? Ix is Ix only. There is no change. Ix. Oh, something. Ix minus of what? What is the first current? Gm into VGS, right? Gm into VGS minus GMB into VBS. Next two. What is the current equation here? Plus voltage. Sorry, what is the voltage here? Ix into Rs equal to 0. First point Vx, the drop across R naught, drop across Rs. Am I right or not? Vx is distributed for this both. Okay. Now what is the VBS here now? What we can write VBS? Can you solve this problem and tell me what it is? This take this equation and tell me what is the Vx divided by x. Take this problem and solve this. Okay, just only take this equation and solve this problem. So here, can you see that VBS? What is the VBS here? Observe carefully. What is the VBS? VBS is actually not plus Vx. Actually, it is coming from so from the source terminal point of view. This is what the plus here. This is what the negative here. Okay, that is the drop across that one. Okay, that means the current enter into this negative terminal actually of the source. You can observe this. The current is coming from the negative terminal of the source. Negative potential. That's the reason why this should be negative. This should be a negative. Okay. Yeah. Go ahead and tell me what is the value of this particular one. Quickly. Equal minus Px plus. This parallel you also do. Ix minus minus plus Gm into Ix into Rs plus Gm into Ix into Rs plus Ix into Rs is equal to 0. If you keep Vx is outside and R naught into RS, if we keep it like this, what happened to this? Let me take Ix also, we'll get a common. And this becomes 1 plus no, this is not the way. Let me keep it inside. R naught into Ix plus R naught into Ix into Gm into Rs plus R naught into Ix into Gm into Rs plus Ix into Rs equal to 0. But I can make a constant. I can make R naught into Ix. So Ix first, let me take it. Ix is common, for instance, because that is what important for us. Therefore, R naught plus Rs is 1. Rs plus R naught into Gm into Rs, R naught into Gm into Rs equal to Vx. Here, Ix, R naught, keep it aside. I can take Rs as a constant, 1 plus R naught into Gm plus R naught into here. So I can also approximate here, approximately Vx divided by Ix is equal to R naught plus, I can make it Rs is multiplied with R naught. Here I can make an approximation, R naught into GMB. This is approximated as, keep it R naught aside, 1 plus Rs into Gm plus GMB. Okay, here also 1 can be less. Therefore, R naught into Rs is multiplied with Gm plus GMB. Yeah, this is what I can say. Please look at this, okay? Please check this, verify this one, R naught into Rs into Gm plus GMB. Class. అయిపోయింది just 5 minutes. Okay. Please verify it at your home. Okay. Please look at this one is R naught. Okay. When the moment if you have the MOSFET, we have a source resistance Rs. Okay. This resistance is R naught is multiplied with Rs source resistance into Gm plus GMB. Please look at it carefully. So this point, okay, the MOSFET will give you this information as well as this information also. Okay, and please try to do it at your home. Okay, and example number 5. It's a very, very important one. This is RD. Assume that this is also connected to VDD and take this one and find the resistance R from the source. Okay, find the resistance C from the MOSFET. So from the source for the given structure. Okay, we stop here today and we will see in the next class.